Yes, you are.
Yes, I heartily welcome you all. Welcome, Mr. Urvish. I would like to introduce our speaker, Mr. Urvish Markert, for the talk on computer arithmetic, how computers do the math. Mr. Urvish has done BTech in Electronics and Telecommunication Engineering. He is currently working as DSP Design Engineer at Xilinx India Technology Services, Hyderabad. He also worked as Research Associate in implementation of spiking neural networks on FPGA at IIT Madras. He also worked as FPGA design engineer at HTIC lab of IIT Madras Research Park, Chennai. He has got the Xilinx Patent Achievement Award for his first invention of approximate fast floating point arithmetic. He has achieved the rank in top 100 in national level mathematics competition, which was held by ISTE and NBHM in engineering mathematics. He was also awarded as the best student of the year by Times of India Pune. He also presented the paper at national level conference on fractional calculus and fractional differential equations. Mr. Urvish also has a strong background in algorithm design for variety of architectures, that is FPGA, CPU, and GPU. He is an expert in mathematical modeling, digital signal processing, vision video algorithms, high performance computing, and computer arithmetic. And I hope you all are very excited for this talk. By the way, yes, our speaker has particular interest in teaching mathematics, so definitely this session is gonna be wonderful. So I request Mr. Urvish Markert to please start the talk. Please, sir.
Thanks a lot, Meg. Thanks a lot for that wonderful introduction. First of all, let me introduce, this is one of my, I guess this is the 25th lecture that I'm conducting till now. I have conducted several lectures, especially in the city of Pune, as well as in Chennai when I was a research associate there. So I do have this habit of lecturing around, helping out the students and understanding their point of view of a particular subject. So this is one of my hobbies which I enjoy doing quite a lot, and hence when I got to know about the COEP Ramanujan Maths Club, I immediately contacted the organizers to held one of the sessions on this. So my particular motivation for why I wanted to talk about computer arithmetic was the very fact that this is something which I've learned, experienced, and have tried and tested. I mean, I do have hands-on experience of this very recently, and I only talk the topics which I know quite well as compared to which I mean as compared to my own self during my bachelor's days. So I only teach and talk about the topics which I'm quite good at. This is a known Feynman technique. So there's a good quote by I guess it is not Feynman, but there's a good quote which says that I mean when one teaches, to learn. So I think we are all learners here. Even I'll get to learn about how my teaching should be improved. And one last thing is um, there's a beautiful quote by Samartha Ramdas himself. He quotes that जे जे आपणासी ठावे ते ते इतरांसी शिकवावे अवघे शहाणे करावे बहुत जन. So that is my motto once again. So let's see how well do I know this topic and how well am I able to teach it to you folks. Thanks a lot once again. Before starting the session, I'd like to prostrate on the feet of my gurus who taught me this beautiful topic and who actually gave me the motivation to learn it in a very beautiful way. So my humble prostrations at the feet of my Gurudev, and then of course Ramanujan is yet another motivation for all of us. Okay, so let's get started. So you can contact me on this mail, by the way. My contact details will be shared later. Yeah. Okay. Yes. Okay. So the outline, I've adjusted the outline of this lecture in quite five different topics. Okay. So first is the aims and objective. I actually visited the COEP Ramanujan Math Club website and I saw what are the aims and objectives of this club. And I got to know that, okay, I do have some shared or aligned objectives, and hence I tried taking this lecture. And another thing is, what is the motivation? Why would you like to, or why anyone would bother studying computer arithmetic? So there are few case studies which I presented that might help motivate you to study it further. And then the third thing is, I'll give you a hands-on approach on, okay, these are some very minute or nitty-gritty details, as you call them. And then which I like to do is, so for me, it is all play, no work. So the fourth topic is how I went about playing around the computer arithmetic, which is, this is something which I'll try to share with you all so that even you can have fun with the same. And fifth, which is the most important topic, is the interesting reads. How interesting you can make it even further. Okay, which is nothing but the references. Okay. So one of the goals of the COEP Ramanujan Math Club is to build a strong mathematics student community. I think we are in congregation. Let us. I actually would like to thank the mathematics club for once again inviting me for this lecture, and to provide opportunities to students to enable them to explore areas of mathematics, right? So, and outside the classroom. So this is quite important. So all the maths which I learned is quite outside. I mean, I learned quite a lot outside the classroom itself. So I think this is quite intriguing aspects of the goals. And the third thing is to support and encourage the study of undergraduate mathematics. So I think this is quite important. So in my perspective, if you have your basics clear, I think you might be able to grasp the advanced stages of mathematics very easily. Okay, so that is one of very important goals of the Ramanujan Maths Club. So my aims and objectives of why am I what is my intentions of taking this lecture. The first thing is I want to make attendees conscious of what floating point format is and what a fixed point format is and what are the compute overheads associated with it, right? Next thing is I would like to give you or I would like to help you understand the mathematics which is there behind that engineering concept. And then after this lecture, I think you will be surely be able to exploit the floating point format with formal mathematical reasoning. And then I'll also provide enough motivation to curiously look for improvements for using the hybrid or custom precision floating points or even fixed point data types. So one thing which we need to understand here is, I mean, you'll get motivated or you will see that mathematics is rather a tool to meditate than just to compute. Okay, so this is a quote by Nassim Nicholas Taleb in his book Fooled by Randomness. I've highlighted this when I was reading the book. So isn't it true, right? I mean, if you see, in true sense, mathematics is a tool to meditate rather just to compute. And the aim of computation is always the insight. So it gives you an insight. The computation helps you provide an insight. So let us first, I mean, let these lines serve as major motivation to what I would be discussing today. Okay, so yeah, so let's start with the first motivation, which is the Ariane 5 crash. If you see, there was one rocket which was built by European Space Agency. It took almost 10 years and USD $7 billion to produce this rocket. Okay, this is just the principal cost of the rocket, but imagine the satellite payloads which it contained. There was one small floating point error in this which took it all down. So just after a couple of minutes after the flight, the rocket crashed down with a very huge explosion. See, these are quite some of the very vividly taken images. I mean, they're not so clear. So if you see what happened here, if you see the major when the tracing back was done, so it happened that the 64-bit floating point number, it was truncated or it was converted down to a 16-bit signed integer space. Okay, so this small conversion and the entire rocket goes down. Okay, So I think this should provide you enough motivation. Like spending $7 billion itself, right? For to understand that, okay, this was a bug is not a joke. Yes. Next, yet another case study is the Intel Pentium floating point division bug. Okay, so what happened was Intel started manufacturing these Pentium processors, and turns out that they found, or they were informed that there happened to be a bug in the lookup tables when someone tried to do the floating point division. So for example, if you this is the division. If you see, if you try to do this division, the answer comes out to be this on this particular processor. These are the erroneous digits, the ones in red, while the correct answer looks something like this. Now, this error was interestingly noticed by a professor, Thomas R. Nicely. If you this is his name, who was again a professor of mathematics. Interestingly, he was actually working on a problem to find whether given number is prime or not, testing the primality, or even printing the primes, or I mean, he was trying to enumerate primes, twin prime numbers using the computer, during which he noticed this flaw. Okay, so this is kind of interesting history that we need to study. Intel, again, I mean, for the people who actually found that their processor was buggy, Intel requested that, okay, you please send us the processor back. We will give you a new updated processor at zero cost. So this was quite a big flaw. Although the only thing which when they reverse engineered this, it seems like there was a lookup table which was actually looking up for the division values for particular scaled down numbers. So that lookup table itself was a bit in error. So that caused this major error to come around. Yeah. Now the important thing here is crazy competitive programming. I don't know how many of you students do this competitive programming, right? I bet many of you are doing it. So a couple of my competitive programming friends, right? I asked them that why do you often tend to use this double float data types, right? And one of them was so notorious that he even replied me with this below meme. Okay. So people they generally try to underestimate what they just try to do it blindly. Yeah. So just because it has a very high numeric range does not mean that you should go about using it blindly to whatsoever application at hand. Okay, so let us let this serve as one of your motivations. That one of the things which I try to uncover today is what is the compute overhead which is associated with these data types, and how to understand them, how to comprehend these ideas, and how to actually apply them in your day-to-day life. Okay. Yes. Okay. So first of all, what necessitated the floating point standard? Okay. So if you see, early men were actually interested in, I mean, as we tried quantifying the numbers, we even tried quantifying it to the huge, as much as huge as we can, and even as low as we could. Right. So mathematicians like Bhaskaracharya have literally formally defined the powers of 10. So just like we have nano, milli, kilo, mega, and some more astronomical units, the Indian number system had Shanku, Padma, Kharga, Visarga, Mahapadma, etc. So these are nothing but powers of 10. Okay, so I have provided a reference over here. I think I'll be sharing one QR code to access this presentation at all. So you can actually take a look at such references which I've embedded within the presentation. Okay, so let's say, you have to represent the speed of light. Okay, so speed of light can be easily remembered if you are aware. It is 3 into 10 raised to 8 meter per second. So would you bother writing it this way, or 3 and then padded with 8 zeros ahead of it, right? So it is up to you, right? What would you choose? I think many of you would incline towards this format because it is easy to remember and easy to write rather than this. So see, focus here that it is easy to write, okay, and easy to remember. Focus on this part because it is only of these reasons that you are going to choose writing the number in this format. Okay, so similarly, if you see, I can associate, let's say, if I ask you what is the speed of light, you quickly associate it with these two numbers, which can be written as a tuple, 3, 8. Right, 3 is nothing but the mantissa, and 8 is the power of 10. Okay, so even if I write it here, it is understood that 8 is the power of 10. Again, similarly, Newton's gravitational constant is 6.67 into 10 raised to minus 11. Right. So even if you remember these two numbers, you are able to reproduce the entire constant. Now, next thing which I would like you to focus on is this. Now, for very easy or thumb rule, we approximate the speed of light using 3 into 10 raised to 8, but rather it is this big number. Okay, I mean, add 2 more digits, it becomes someone's phone number. Don't try calling it, right? Hello, speed of light speaking. Okay, so yeah, so understand that why we try to uh, memorize that number in this format rather this, because it is easy to remember, right? Who try to remember this 2.99792458, right? Nobody. Now, yeah, so now the going to the fixed point arithmetic. Now what fixed point arithmetic does is this. Fixed point arithmetic is something which is very native, the one which you learned in your high school. So it assumes that the decimal or binary point is fixed. Okay, so either the number is 2.3, 1.3. Okay, that means the decimal point is fixed, and the programmer, he or she actually tries to assume that point in mind and then continues the entire data part design using integer arithmetic. Okay, now one quick thing to notice here is, let us say computers, they actually handle the digits in binary fashion, right? Because they're nothing but at the end they are all transistors. They're all switching on and off, switching on and off. So that is how computers are working for us. So at the end, all the numbers, be it decimal, floating point, anything, they are all represented in binary. And for binary arithmetic, one thing you need to understand here is that, let us say if I want to add two numbers, x1 and x2, and I want to store it in, let's say, y, then what should be the bit width of this y such that I can faithfully store the addition of these two numbers, right? So it is given by this. So the formula to compute that is very easy. So you take the max bit width of any two operands, I mean, not any two, but yeah, max bit widths of these input operands, and then add 1 to it so that this one prevents the overflow. Let us say you have 8-bit numbers, right? So the max value it can achieve is 255, 255. Let us say if you add those two numbers, you get a number which is beyond 8 bits. I mean, you need more than 8 bits to store it. So what better number, what number you can store it in? It is +1. So 9 bits number is required if you want to add two 8-bit numbers. Okay, now similarly for multiplication, what happens is, it is quite intuitive that you can understand. For multiplication, it is rather addition. So let us say if you want to add two 8-bit numbers, then you would require the word length of the output to be exactly 16 bits. Okay, so this is something, a rule of thumb that you need to understand. Now you would ask me, this is for addition or subtraction, right? Addition and subtraction goes hand in hand, because if you remember, subtraction is nothing but addition with 2's complement of the subtracted number. Okay, even multiplication is very easy and comprehensive. You would rather ask me, what about division, right? So it is quite fun that how would you go about deciding the word length for the output. For that, I have pointed you to this beautiful reference. It's a fixed point arithmetic paper. It's designed by Randy Yates. So he's the person who is actually behind the Motorola processor, and he's quite a DSP guru. I've learned quite a lot reading his papers. Okay. Okay. Now circling back to the IEEE 754 floating point standard. Interestingly, I would like to just give you a brief history of what this standard, what is the history of this standard. If you see, if you try to search it over Wikipedia or something, you'll understand that this was actually invented by a civil engineer. Okay, so his name was I think Conrad Zuse. Okay, that guy he actually formulated this format, and then there's yet another professor. His name is Professor William Kahan. He again tried to make some changes in this. So he's a professor of computer science and electrical engineering at University of California, Berkeley. Okay, he's still a professor. I think he is 88 years old. So these are the folks who actually tried shaping it. And there was yet another fellow called Dan Zuran. He was a fellow at Hewlett Packard, and he has spent 18 years of his life formulating this format. Okay, so it's quite interesting. Even if you try to study the history of this floating point format. Okay, so coming back to the details, if you see the floating point format has three fields. The first is the sign bit. Okay, so this sign bit helps you decide whether the number is positive or negative. Okay, so for positive number, the sign bit would be 0. For negative numbers, it would be 1. And then there is this yet another field. The next field is for exponent. So it contains the exponent, just like the format which I explained you, right? So if you remember the speed of light, it has 3 into 10 raised to 8. So 8 is nothing but the exponent, and 3 is the mantissa, right? So you would store 8 here, and then mantissa, let's say 3, will be stored here. Okay, and what would be the sign bit for the speed of light? Of course, it would be 0 because it's a positive number. Okay. Yeah, so far so good. Okay, I think everyone is with me, right? Okay.
Yes.
Okay, cool. Okay, so what happens here is it is also called a mantissa / fraction, because literally it stores a fraction rather than entire mantissa. Okay, so mathematically, if you see a floating point number which is stored in this format is represented using this formula or this equation, x equal to -1 raised to s. Okay, so if s is 0, this would automatically become 1 and would imply that it's a positive number. If s is 1, this would become a negative number, as simple as that. And then this is multiplied by, 1 plus m small m raised to, small m divided by 2 raised to capital M. Now, what is this capital M, capital B? Okay, so let me give you a brief overview once again. So capital E is nothing but the number of exponent bits. Okay, and capital M is the number of mantissa bits. Okay, that is required to store a floating point number. Let us say, so any floating point number is stored as 1 point something. So that fraction is stored here. 1 point, let's say 110110. Okay, that's the fractional part of it. It is stored here. Only that fractional part. Okay, because understand that this one is not stored anywhere. Okay, so it is 1 point something divided by 2 raised to m. So why have I divided here with 2 raised to m? Right. So if you understand, if a normal decimal arithmetic also, if you take it as 10 raised to m, so that would mean I would shift the decimal point m places below the this original decimal. Okay, so this means I'm placing this binary point. So here it is not the decimal point, but the binary point, it has been shifted by capital M places. Okay, and hence it is 1 point something. And this is 2 raised to e minus b. Now what is this e? E is the exponent. In the speed of light, 3 into 10 raised to 8. So 8 happens to be the exponent. if you convert it in binary, this is what is getting stored. And there is some bias which is added in order to represent the signed exponent values. So we'll circle back to that later. Okay, so basically this is the equation. I need you to understand this equation first. Okay, so again, M is the mantissa equivalent or the mantissa um, in decimal equivalent of this binary number which gets stored, and E is the decimal equivalent of exponent that gets stored over here. Okay, yeah. So let us say for there are various floating point standards, right? One of them which is very most often used is the floating point 32 or the float standard if you use, right? So it has 8 bits of exponent and 23 bits are allocated for mantissa. And as for the double, which is yet another popular data type, and even softwares like Python, C, not C, I mean C is strongly data type language, Python or even MATLAB, Java, they try to use this as their default data type. Okay, it has exponent bits are, exponent bits are 11, mantissa bits are 52. So see here, just because the size is double, that's the naming convention that they followed. There is yet another custom data type which is called FP16, which is the 16-bit floating point format. It has 5 bits of exponent and 10 bits of mantissa. So if you add them, you'll see that okay, it adds up to one less than the 64-bit or 32-bit standard. Then if you remember, one is nothing but the sign bit. So that is assumed by default that there exists a sign bit. And if you add them, that comes out to be that specific number. Okay. Okay, moving ahead. So if you see floating point format, if you understand it, is all about the dynamic range. Okay. So what is dynamic range? Dynamic range is a, I mean, it's roughly a measure of how many numbers can you represent using that particular standard. So for integers or our normal mathematical pen paper based mathematics, the dynamic range for integers or reals is infinite, right? So mathematically it is defined as a ratio of max positive number that you can represent with that particular standard divided by the minimum value or minimum positive value you can represent with that particular standard. So let us compute the dynamic range for reals. So for reals, the max positive number I can represent is infinity, and the minimum positive number which I can represent is some 0.00000001. Again, if I divide them, that division of 1 over 0.00001, whatever it is, it again, if you take the inverse of that, it becomes again infinite. Infinite again multiplied by infinite becomes infinite, right? So that is something you need to keep in mind. Now the dynamic range of fixed point numbers, let us say you have 8-bit numbers, 3-bit numbers, 4-bit numbers, whatever. So the dynamic range of that fixed point number is actually, I mean, it is approximately equal to 2 raised to b, where b is the number of bits allocated for that representation. Okay, now understand that, let's say if you have 32-bit fixed point number, what would be the dynamic range? It would be roughly 2 raised to 32. Okay, it's still a huge gigantic number, but not not the one which we are, I mean, which we are very interested into. I mean, for applications which comply within this dynamic range, you can surely go ahead and use this. And rest for others, let us understand the dynamic range of other numbers. Okay, so dynamic range of floating point 32, if you see, it is like such a huge number. It's 2.909 into 10 raised to 76. Okay, and for 64-bit floating point number, it is even larger, and it is 0.806 into 10 raised to 616. Okay, such huge numbers. It is almost infinity. Okay, I mean, it's countably finite. Okay, countably infinite. Now I would like to understand that you would ask me how this dynamic range comes in play, and then you would ask me how to decide whether what format to be used for which numbers. Okay, or rather for what application. So if you see digital system design, there happens to be one processor, and that processor gets some digital data. Now, how does that digital data comes to the processor first? Okay, if you see the data interfacing happens often using a transducer. Okay, and that transducer is nothing but it converts some physical quantity into an electrical quantity, and that electrical quantity is again given to processor for some computation. Now, how does that happen? Simple, using ADCs, right? ADCs means the analog to digital converters. So if you see that the ADCs they actually have limited output range. So either the ADCs, classically the ADCs would be 8-bit, 16-bit. Okay, I have never seen ADCs more than 16-bit. Some applications demand, but I have never seen more than 16 bits. Okay, so that means the data which is quantized itself is coming to the processor in 16 bits. Then why bother using the numbers? I mean, if you see the input data itself would be in 16 bits, then why would you bother to use floating point formats at all, right? You can, at max, you can use unsigned or signed 18 bits, and you're good to go. Okay, so first thing, what happens here, let us say if you understand the data type for a particular application, what happens, we will explore that later, that you tend to save a lot of power and lot of compute density, because the data path itself is trimmed for that particular application. And as a result, the silicon footprint or the hardware footprint that it results into is quite manageable, or it is less than what you would get using the floating point implementation. Okay, naive way of going about doing it is just using floating point number and then getting it done whatsoever. Okay, so let us not do that. Yes, okay. Now, one thing you would ask me is, let us say, even though all the digital data that is coming to us is all quantized using EDCs, then you would ask me what has necessitated this floating point number, right? So it is mostly, I think it is, if you see processors like even NVIDIA's GPU and all, they are inherited. I mean, the data path itself is implemented such that it is, it is implemented assuming that the number will be in floating point 64 format or the double format. Okay, so what happens that, okay, although the data that we get is in digital format, but applications like scientific computing and all, where you have to do interpolation. So what you do is, although you get a digital data, you try to interpolate it, and then you get some exact values or some very near about values, wherein sometimes high precision is required for space applications, for medical applications. Very high precision data is required. Okay, so that is where you interpolate the digital data, you try to get much information, more about that, and then you go about doing things. Okay, that is how these numbers come into picture. Okay, so mostly if you see scientific computing related applications, they demand the use of floating point arithmetic. Okay, because they don't want to compromise on accuracy whatsoever. Okay, so how the data path is implemented, you would ask me. I would like, here I would discuss I would contrast how the data path is implemented for floating point and a fixed point. Okay, so first things first, let us establish that there exist some basic compute primitives for arithmetic operations like addition, subtraction, and multiplication. Okay. So if you are familiar with FPGAs, the field programmable gate arrays, there are some specialized cells which are embedded into FPGAs, which are called DSP cells. Okay, so these cells are nothing but these are hardened blocks, or it's almost a specific chip, or a specific silicon, which helps you multiply, add, multiplication, and addition just within one clock cycle. Okay, so let's assume that there does exist such entities. Now we now how how to go about extending this format for floating point. Okay, so for fixed point, as I told you earlier, it is all nothing but the high school arithmetic. So let us say for fixed point, it is because the fixed point is quantized and the input is in limited dynamic range, then you can easily go about doing those operations whatsoever. Because if I say, let us say I have 16-bit number. Okay, so you would assume that okay, the max it can result is the multiplication can go is like 16 plus 16, right? The multiplication output will have 32 bits. Okay, these are all, I mean, this is something which is very intuitive and comes just like as you learned your high school arithmetic. Okay, but for floating point, this changes. Okay, I'll give you an example. So let us consider that this famous mass energy equivalence, which is E equal to mc square. Consider a mass of 2 gram. Okay, and then speed of light is okay. I've approximated it here once again for ease of use. If I expand it, this is something which I get. Okay, so first understand how multiplication is happening here. Okay, understand that these numbers like these, they require floating point, and how are they getting multiplied? Okay, so for how I would like to go about doing this is multiply the mantissa 9 and 2, and because these are powers of 10, let us just add them. So it is as simple as that. I'll multiply it with powers of 2. I mean, multiply the mantissa and then add the exponents. Simple. Now let us understand how addition goes. So for that, I've taken an example of Kirchhoff's law. So if you have 3 current streams, one is 2 milliampere, one is another is 1 microampere, and the third one is 1.99 milliampere. And you have to add them. I mean, you have to prove that, okay, Kirchhoff's law holds there. So how would you go about doing this is, let us say, because even if I write it in I mean 1 microampere, I have to normalize it such that I have to meet other units as well. Okay, hence I have written it in this format, that I have normalized 1 microampere as 0.001 milliampere. Okay, understand that this normalization involves some overhead. Okay, although this is a mental overhead, in computer, it actually results into some hardware overhead. Okay, and then I went on adding this, and this is how I proved that Kirchhoff's law holds there. Easy? Okay, so far so good. Now the hardware implementation, if you see the computer, inside a computer, it is actually implemented the same way which I taught. Okay, so mantissa digits are getting multiplied. Okay, exponents are getting added, and then this bias is getting added, if you remember the floating point number, and then that is getting stored, and the sign bit itself, there is an XOR logic. So if A is positive, B is negative, B is negative, or B is negative, A is negative, and so on. So in order to handle that, this simple XOR gate can be implemented, and that is how a floating point multiplier is designed. Okay, understand? Okay, but understand that floating point multiplier is easy to comprehend, but when it comes to floating point addition, it is quite difficult. Okay, because if you see, I had to normalize this particular number, and then I mean normalize as compared to other operands, and then I had to add them. Similar way, it is also implemented in hardware. Okay, the exponents are subtracted, and then this logic tries to define whether okay, which number would I have to shift. Okay, so division is nothing but shifting operation in computers, and then addition of those significant digits happen, and then the exponent is getting adjusted, and that's how the result is implemented. Okay, that is how. So one thing you need to focus here is floating point addition is expensive, quite expensive than floating point multiplier. Okay, although it involves a multiplier cell over here, you might argue that okay, this is O of n square complexity, but when it comes to fetch and then process instructions, I think that overhead here in this hardware is quite huge than the floating point multiplier. So there's a beautiful reference which I would like to point here. It's a book called Computer Organization. Many of you might have already read it, by Karl Hamaker and then Safawat Zaki. Our teacher used to call it as Zaki all the time. Okay, it's quite an interesting book. First of all, if you see the cover itself, the cover has a very abstract painting, which I hated at the very first attempt. But when you try understanding, or if you try working out that book, it's actually a book which is worth falling in love with. Okay, so I think the attendees here, especially those who are having their computers and electronics as majors, I would definitely request you to at least have a give this book a quite thorough try. Okay, so now coming back to the fun part, which is a recent innovation. So recently what happened here was that Elon Musk, he started discussing about these floating point formats. Okay, so there's this tweet which you can go about analyzing. I'll keep those details to you. Yeah, okay. So now what we will do is we'll try to understand the recent innovations. That why am I actually interested in taking this talk? Okay. So if you see the recent papers have actually started revisiting the floating point numbers, and they have understood that let us because the training and the inference or even the retraining of neural networks consumes so much of power that you need to understand, or you need to go back to the implementation of, okay, let us do something about it. Okay, so see here, so these in this paper they actually trained a deep neural network with 8-bit floating point numbers, and here they claim to have achieved that. Okay, they have got 2 to 4x improved throughput, okay, as compared to their baseline implementation using 64-bit or 32-bit floating point number. Okay, so see the first line, the opening line itself, the state-of-art hardware platforms for training deep neural networks are moving from traditional single precision computation towards 16 bits of precision. Okay, understand that, okay, there has been a trend that people are actually moving towards a configurable floating point number, which actually results in a very efficient silicon throughput and a very low silicon footprint, and more importantly improved throughput. Okay, and that too by a factor of 2 to 4x. Now this entry was actually accepted at NeurIPS 2018. Okay. Okay. Now even the scientists at FB, or the Facebook Meta, whatever you call it, they are actually very more keen about how to go about um, or how to go about rethinking the floating point format. So there's this person called Jeff Johnson. He's a single one-man army guy there at Facebook Research, and he has published quite a very quality articles which are worth reading. So he has, in this paper, he has actually proved that using new or some mathematical schemes like logarithmic number systems, right? If you use logarithms with these floating point numbers, it becomes even more easier. So he has actually proved that his implementations have become more energy efficient, and then equivalent to that of, or even more energy efficient than equivalent bit width integer hybrid log multiplier. Okay, and he has even proved that there is no network retraining that required. Okay, and one more metric which he discusses, that the area or the silicon footprint has reduced and even the power is reduced. Okay, so this is something which you need to keep an eye on, that okay, changing the data types itself helps quite a lot. Then why to go about using unnecessary silicon for just for trivial applications? Okay, there's one more very beautiful paper by Xilinx. So here they have actually proved that higher performance of neural networks with small floating point. Okay, so small floating point is the definition of 8-bit floating points. Okay, So here they have actually, see here, they have literally mentioned that they have outperformed Intate on some Xilinx hardware without loss of accuracy or retraining. Okay, so here, I mean, for inference, if you see, majorly for inference, integer data type is preferred, and for training, floating point format is used. Okay, that's a rule of thumb to go around. Okay, so here they have actually they have not compromised on performance, but rather they got 60% performance improvement. By performance, I mean the throughput was improved quite a lot. I have even given a reference link over here, and you can actually take a look at it. Okay, so it's quite an interesting paper. Okay, now the very fun part, which is the Tesla Dojo. This is what Elon was discussing about in that Twitter thread. So all these people, they tried working out, okay, what floating point needs to be improved, how floating point needs to be improved. This fellow, on the other hand, the Tesla team came up with a very beautiful idea, which is configurable floating point number. Okay, so they actually came up with a they actually orchestrated that floating point format such that you can play around with each and every fields of that, and it gives you more degree of freedom to go about playing it. Okay, so if you see, there's a enormous pressure on memory storage bandwidth and storing the because storing the weights and activation function and the gradient values. So if you come, or if you quantize it for given that you have a brief idea, okay, what would be the dynamic range of that particular numbers, then you use it, you use a particular data type for that application. Okay, and so it guarantees an identical numerical result. So this is the main important point. So here they discuss that one key property enabling this configurability is the fact that different parameters like weights, gradients, and activations have different precision and dynamic range requirements. Okay, so now you go and you see, okay, what can be done for each and every application. And okay, so for weights, gradients, and even activations, the dynamic range differs quite a lot. And to achieve high training accuracy and convergence, the configurability enables different allocations of the number of exponents and mantissa bits depending on the parameters being represented. Okay, so it's a bit of you might find it, okay, this is a very heavy dose of technical details, but I bet after this talk, if you revisit this paper, I bet you will be able to make heads or tails out of this for sure. Okay, now moving to the last application, which is the fun application, which I would like to discuss here, is the Quake 3 fast inverse square root algorithm. I first learned it from Mahesh Venkatachalam. He's a founder of Electronaut Labs at Bangalore. So he shared one link to the YouTube video explaining this on Twitter. So I've embedded a link to this YouTube video over here. You might want to go and revisit that. So let us say you want to compute inverse square root of a floating point number. Now, how does a computer do that? And how can you efficiently do that? Okay, there was one programmer who actually came up with a very brilliant idea, which is what we are going to discuss now. So let us say that x equal to -1 raised to s, and then this entire floating point format equation, which I explained earlier. If I take a binary logarithm, I mean, why would I go about doing this? So, and trust me here, okay, for no mathematical reason, I take binary logarithm of this. What happens later on, if I try to simplify this, I get a very beautiful equation, which is binary logarithm of floating point number x is it is approximately equivalent to the bit representation of that floating point number, if you were to convert it into integer, divided by 2 raised to m plus mu minus b. Okay, so this is now, if you see this 2 raised to m, this division can be achieved with a simple shift register. I mean, it can be simply shifted right, and then that division can be taken place. And this is addition and subtraction of fixed point numbers. Here mu is a predefined constant. Mu is generally taken to be as 0.043 or even 0.5, depending on what is your error tolerance. Mu is just a statistical parameter which you would like to tune for your particular application. Okay, let us understand, let us assume that it is constant for now. So the key approximation which I've used here is binary logarithm of 1 plus x, where x is assumed to be very, very less than 1, is approximately equal to x plus mu. Okay, only if I assume that do I get this. Okay, now next thing. Now because we want to compute inverse square root, I'll take y is equal to 1 over square root of x and then take binary logarithm at both of its sides. Okay, what I have here is this. It's a beautiful equation called bit representation of y, or floating point bit representation of y, is approximately equal to floating point bit representation of x divided by 2. This again division can be achieved using simple right shift, plus addition of some constant. So this capital M is nothing but the mantissa bits, the number of mantissa bits for that particular floating point standard. Let's say you use FP32, then this would be 23 bits. Okay, so this M would be nothing but 23, and B is the bias. Bias is a constant value. Generally, it is taken to be as 127 for FP32, and mu is 0.5 or 0.043, whatever. Okay, so let us understand the code, a very intelligent code behind this. So if you take float and then you define this as a function wherein the input operand is expected to be a float number. To convert it, I mean, this floating point number is stored as a floating point number, but is read as if it is stored as an integer. Okay, so this is a very evil floating point bit level hacking. Okay, so it is, although it's a floating point number, but this piece of code enables, or this piece of code actually helps it read it as though it's stored as an integer. So by this you are actually extracting the integer equivalent of bits that are stored in that floating point. Okay, and then this number, which is nothing but this magic number, they call it as magic number, which is this constant, this particular constant, subtracted by I right shifted by 1. Okay, why 1? Because this, the power of 2 is 1 here. Okay, and then again this input or the value is read as a float, or as if a floating point number was read, and some additional Newton-Raphson iterations are added over here just in order to add some more bits of accuracy. But understand here that all these Newton-Raphson iterations, they don't have any other major non-linear operator here. So they do have a simple multiplication and one subtractor. That's all. Okay, so you can add some more iterations of Newton-Raphson, but that's up to you depending on the level of accuracy that you want. Okay, I think that's it. I hope you like this application particularly. It's quite an interesting application. It has motivated me for my own patent, which I recently submitted. Okay, these are some of the interesting reads which you can go about reading. I highly recommend reading the IEEE 754 floating point standard, and even there's this beautiful book called Primes: A Computational Perspective. It is actually called Black Bible for those who are actually interested in cryptography and related applications. Okay, and fourth is again an interesting book which has motivated me to actually understand mathematics for engineering. It's a very interesting book by Dean G. Duffy. He was a professor at US Army. And one more book is Computers as Crucible. Okay, it's quite an interesting read, how computers can be used for particular compute related applications. Okay, I think that's all. You can get in touch with me here. The access to this PPT is quite open, and I've added a QR code here. You might feel free to take a screenshot and then access it later on. That's all. Thanks a lot, folks.
Thank you. Thank you, Urvish, for such a nice, deep, and detailed and interesting talk. Any questions or any comment? Anyone? So this meeting has been recorded, so I will share the link with Urvish you as well. And
Thanks
if
a lot.
anybody wants to see the recording, they can request Mahek. Then she will share the link with you. Okay, so if no questions, then I would like to request Mahek to please give the vote of thanks.
Thank you, sir. Thank you so much, sir, for this wonderful session. Thanks a lot. I feel the motivation which you have presented at the start, the Arraign 5 crash and that bug in Intel processor, that has really attracted the audience for the whole presentation. And then
Thanks
the
a lot.
presentation was wonderful, sir. Thank you so much for the wonderful talk. And I would like to show my gratitude to Vice President of Gymkhana, Bhavikatti ma'am, for giving us permission to conduct this lecture. I'd also like to thank Dean of Student Affairs, Dhamangaonkar sir. I'd also like to thank Faculty Advisor of Ramanujan Mathematics Club, Dr. Jatin Majithia, for always guiding and supporting us. I would also like to thank Associate Professor at Department of Mathematics, Mrs. Yogita Mahatekar, for sharing the details of our speaker. And last but not the least, I would like to thank all the audience for attending this lecture. Thank you so much, everyone.
Thanks a lot.
Yeah, thank you. Thank you, everyone. Thank you, Urvish.
Thanks. Thanks a
I
lot,
will share
Jatin.
the link with you. Okay. Yeah. Bye bye.
Sure.
Take care.
Bye. Good night.
Good night. Thank you, everyone.